Lesson number 3. If we look, I've taken this diagram and I've kind of like put some frame to it. This was known as Young's experiment, double slit experiment. Notice we have 2 slits. Now, the length of the race is very important to us. So what I've done is made a couple frames here. We have the distance, we call it D. That's the distance between the slits. Now, if you're running a race, does it matter how far apart the things are when you start? And the answer is sure it does. You know, the wider they are, people are going to have farther to run as we go on some kind of angle. Now, I'm going to do a little math trickery here. So what I'm going to do is draw a line here from this spot to here, and then draw a line straight across like so. The angle on the top, we're going to form some type of triangle here, the right angle being in this corner. The angle we're going to measure is here. We'll call that theta up in the top part of the corner of the triangle. All right, now I'm interested in this path length across the bottom right here. And the reason why I'm interested in that, isn't that the extra distance that the bottom wave has to travel when it's on its journey to point P? So if we start the race, ready, set, go, isn't this wave on the bottom actually behind the other one automatically? So what I've done is kind of even them out using this leg of the triangle. And in this case, the race would be even. Well, guess what? It's not even. All right, the bottom one is set back this far and has to run this much greater distance. So ready, set, go, go. So the top one arrives first, and then the bottom one has a longer race to run. So we've got to take into account that extra distance. Now, if I look at this triangle, D is the hypotenuse, and that's the angle. So this is the opposite side. So we know from trig that the opposite side is D sine of the angle. So you take the hypotenuse, sine of the angle, and that gives you the opposite side. That's just basic SOHCAHTOA. All right. Now, if we look at this extra distance, D sine theta, that's the distance extra that the bottom one has to run. Now, if this distance it has to run is a whole wavelength, aren't they going to end up matching up when we get to the end? So, for example, if I have a wave, I don't actually have to hit each peak here, but can I hit the next peak? Well, what's the distance between these peaks? One whole wavelength. So, as long as this distance here, the extra, is the same as a whole wavelength, they're always going to match up, and then this will cause them to be peak to peak. So as I draw them, this will be a peak. This bottom one, as long as it's a whole wavelength, will also be a peak, and we'll end up with a bright constructive interference. So this nice formula that we have here, d sine theta, the extra distance, is equal to the wavelength. Now we can modify that slightly. It wouldn't just have to be one wavelength off. Couldn't it actually be 2 wavelengths? Or perhaps 3 wavelengths, 4 wavelengths, etc. So if I look, I can modify the formula. D sine theta, that extra distance, could be off by 1 wavelength. It could be 2, 3, 4. So instead, I'm just going to put a number here. So a letter. And M is called the order. And the order could be number 1, it could be 2nd, 3rd, 4th, 5th, along those lines, all the way out to infinity. So if it obeys this law here, we know that we're going to get bright, and it's going to look very bright. Where? It's going to be a bright spot right on the screen at that spot if it's whole number multiple.